But for now, let's continue with this example and let's see what R finds, how R finds those splits. We're gonna use this tree library to find a tree model, and inside tree library there's a tree function. And the syntax of this function is very similar to LM or GLM function, so you provide a formula here, and here we regress the salary in the logarithmic scale to the years and the number of hits. We use the hitters data set. And then we do this prune.tree operation. I'll explain a little bit later what it does, but essentially we say we want the tree of size 3, which means that we want 3 regions. We want 3 regions. And now we know that 3 regions seems like a good thing just because we looked at the data already and the data can be plotted, and we try to do this mental experiment where we try to define those regions, and 3 seemed like a good idea. So here we just specify that we want tree with 3 regions. Later we will learn how to define how many regions you want without using this visualization trick. And then we use this plot command to plot the tree, and the text command will put those labels. And so it's actually slightly similar to what we found, right, in our previous plot. So if years of experience less than 4.5, then it's going to be 1 region of the tree. And if it's greater, then you subsplit into 2 other regions if the hit's less than 117. And what you see here, those numbers, those are the averages. So this one, number 5, is the average salary, again on the logarithmic scale, so it's 10 to the power 5 is the salary, is the average salary of all of the players that fell into this region 1. And this is average salary of all of the players in region 2, and average salary of all the players in the region 3. All right, so now you see this command partition.tree, and it basically will build the partition associated with the model. And now we try to replicate the same image as we did manually. We have 3 regions, region 1, region 2, and region 3, and inside each of those regions we find the average. So this is y1 bar, y2 bar, and y3 bar. And now the way we're going to do the regression, you're going to give me a new point. So you say I have a player with 15 years of experience and 200 hits. So I say, okay, 15 and 200, this player going to end up here. And now if you ask me to predict the salary for this player, I'm going to say, okay, my prediction y hat for this player is 6.7. That's it. That's how I define the model, and that's how I use this model for the prediction. Okay, and now you can see this plot side by side. So we can either graphically represent the split into the region, so we can do it as a tree. Again, this only works if you have up to 2 inputs. After that, you cannot do graphics, so the only thing you can do are those tree-based representations of those models. Okay, so this is a formal definition of how we do the prediction now. We use this indicator function. Let me define the indicator function. So indicator function, and here inside the indicator function takes some statement, okay, and the indicator function returns 0 if this statement is true. So if x does belong to region J, sorry, not true, and it returns 1 if this statement is true. It's a 0-1 function which basically converts, checks whether this one is true or false. That's all it is. And again, the way we do the prediction is we say, okay, if you give me a new data point, then I'm gonna, that's a very convoluted formula. Essentially, we say f, so the way we do it is following. So if x belongs to region J, then our prediction for this x is just yj bar, where yj bar is the average across all of the y's which correspond to the x's falling into this region, as we talked about this before. Okay. Now we need to define some formal criteria of how we build the tree, and formal criteria usually comes in the form of the objective function that we try to optimize. And there's nothing special about tree models. We try to optimize this residual sum of squares, the same criteria we used for linear models. So what you see here in this formula, we compare the difference between yi, the actual observed value of y, and yj bar, which is the predicted value of by the model. And when we take the square of this difference and then we average out across all of the x's, but we write it slightly different. So we say first we have two sums. So we sum across the regions. So we have j regions, and we take one region at a time. And for each region, we take all of the observations that fell into the region, so indices I that correspond to the observations in this region, and then we take the difference between y and yj bar, which is the prediction associated with this region. So essentially, it's just residual sum of squares, and then we try to minimize it. Now, unlike in the in the linear regression problem, this objective function is not easy to solve. More specifically, it's actually NP-hard, which makes this problem very hard to solve computationally, and we can only solve very small instances of this problem, meaning that we have a small data set. The moment your data set goes beyond, let's say, 100 observations, it becomes relatively hard to solve those problems. So, and actually, till nowadays, we don't really know how to solve those problems efficiently. So this minimization problem is not the minimization problem we're actually going to solve while we're finding a tree, but we're going to be solving something else. And we're going to apply what is called a myopic approach. And the algorithm that does solve this problem using this myopic shortcut is called the CART algorithm. CART algorithm, instead of solving this problem, it finds a good enough approximation to the solution of this problem. And this good enough approximation was shown in practice to be working relatively well. So instead of actually solving the problem, we do this shortcut and just use whatever solutions come out of that. Okay. So let's summarize things. So all observations belong to a single region, and we successively split the predictor space. Successively means that we find one split at a time. That's what CART algorithm, and that's the myopic part. Instead of finding this all of the optimal splits simultaneously or jointly at the same time, it does one cut at a time. Okay, and one cut is relatively easy to find. And so each cut or each split creates two new branches of the tree, right? So once you divided the region, you will have one branch that corresponds to left side and another which corresponds to the right, so or top and bottom if you divide in this direction. The algorithm, as I mentioned, greedy or myopic approach, meaning that it does one variable at a time instead of considering all of the variables at the same time. And at each iteration, we decide on two things: which variable j to split and the split point s. So if you have p-dimensional input, you have p variables to choose from, and then you have to decide at which point in the range of this input variable you need to perform the split. And then once you decided on this, then you define two regions. One region is where this variable xj less than this decided value s, and the second region where those values of x are greater than this value s that you decided. And the way we decide on this j and s is by solving these optimization problems. So let's look at this. So you try to minimize, and you try to minimize with respect to j and s. So j is the index of the variable, and s is the location where to split. So imagine you have, your x1, x2, x3. Okay. So first you decide which of those x1, x2, and x3 you split. So let's say you decide you're gonna split on x2, and then you define at which location So, you know, you can split x2 here, x1 here, x3 here. So that's basically your search space, which variable to split, and where on this line this variable needs to be splitted. And again, so the way we decide on this index j and location of this split is by minimizing this sum. So what we want, once you split it, the input space into those two subregions, region 1 and region 2, you want the variance, so that you look at the variance among y's, or root errors squared. When you sum them up, you want them to be as small as possible. And you sum up all the errors in region 1 and errors in region 2. And you want this total sum of two errors in the two regions to be as small as possible. So again, this is just deviations between observed y's and the predicted y's. So remember, y bar 2 is the prediction that will be done by the tree model, and then we just square those deviations and we sum across all of the observations in both of the regions, and then we sum two region errors together, and the minimum of this will be the one that we're looking for. Okay, now the question is, how do we do that? How do we do that? And actually, this optimization problem involves this discrete variable. So this index j here, index j is integer. Okay, and so if you take an operations research class or some optimization class, you'll know that those integer programming problems are very hard to solve. So instead of solving this integer programming problem, we're actually going to solve it using brute force. So we'll solve using brute force. How are we solving this using brute force? Well, we try all possible j's. So let me write here. Try all possible j's. So you basically do one variable at a time, okay? So you take 1, so you take x1, and then you have to find this point s, at which point to split. And there is actually the way, and then you try all possible s. Well, in theory, s is a continuous variable, so trying all possible values of s doesn't make sense. But in reality, our dataset has very specific observations of x1, right? So if you look at your x1, there are going to be a few points on this line for which you have observations. And so the algorithm only will try to split at those locations. So let's say this is your first observation, this is your second observation, and this is your nth observation. So the algorithm will try n possible locations to split the variable x1. And then it will calculate this number here. So essentially, if you have p variables and you have n observations, then algorithm will calculate p times n splits, and then you compare this value of this objective function for all of those p times n splits, and you pick the one with the smallest value of the objective function. So that's what it means to solve it using brute force.